Good afternoon to all of you. Now we have a session on remote sensing applications for geological studies. I am Rajat, Dr. R.S. Chatterjee from the Geosciences Department of Indian Institute of Remote Sensing. Geology, geoscience or earth science, it deals with the science of rock types or lithology of the solid earth, geomorphology or shape of the earth surface, and geological structures or tectonics in the earth crust. And a variety of physical, chemical, and tectonic processes are responsible for molding the shape, composition, and structure of the present earth. And these processes are still continuing, maybe at a lesser degree. Now you see the earth has a layered structure. It is made up of essentially 3 layers. You can see the illustration on the right side. This outer layer is the crust, then the mantle, and the inner one is the core. Of course, core has 2 divisions, outer and inner core. We are not going to the details of the earth interior structure. Now this outer part of the earth is known as the lithosphere. And this lithosphere, it consists of the crust and a small part of the upper mantle. And this lithosphere is not continuous. It is broken into pieces. And these pieces are known as the tectonic plates. These tectonic plates are of different sizes. Some are very large and some are small or minor plates. Now these plates move, they interact with each other. And this is essentially driven by the convectional forces. And this force, it is coming from inside the earth. And the tectonics of the earth crust or the geodynamics, or rather the restlessness of the earth, this is explained by the plate tectonics theory. There is a theory, it's known as plate tectonics theory. Now coming to the next slide, see these in plate tectonics, we have 7 major plates and there are many minor lithospheric plates. The major lithospheric plates like Indo-Australian plate, Eurasian plate, African plate, the North American plate, South American plate, Pacific plate, and Antarctic plate. And there are many minor plates. Now, how we will come to know these plate boundaries? You see, there is these important findings. These geographic locations of the earthquakes, you see here it is shown on the illustration below by this SM and this some H means it is deeper one. So these are basically the locations of the earthquake epicenters. Epicenters means that is at the horizontal surface. There's the location of the earthquake deep inside the earth crust. Now you see the concentration of the earthquake epicenters, basically they define the plate boundaries. And there are thousands of small earthquakes that occur every day. And globally, there are medium to large earthquakes. That means magnitude from 6 to 8. They occur on an average once a month. And there are some earthquakes in this Himalayan region of around 5 magnitude earthquakes. There are 2, 3, and different parts of the Himalaya. And these are the magnitude of around 5 or so. But this medium magnitude earthquake, which occurs once in a month on an average, and strong earthquakes means where the magnitude is greater than 8, they occur once every year on an average. Now you see here the plate boundaries can be easily delineated based on these earthquake epicenters. But does that mean that only earthquake occurs only at the plate boundary? No. It occurs mostly in the plate boundary, but it is not that earthquake does not occur inside the plates. It occurs. Now coming to the basic remote sensing applications in geosciences, let us define first remote sensing. Although we have studied a number of previous sessions more about remote sensing techniques, theory, and the data processing. So now you see once again, let us brush it. Remote sensing is the science of sensing earth and also planetary objects. Nowadays, we are doing a lot of planetary remote sensing. Okay, so it is remote sensing is the science of sensing Earth and planetary objects from a remote distance based on electromagnetic radiation, and that is received from the objects. So how we receive it? We receive it from the platforms. The platforms can be a satellite, can be an aircraft, or it can be a drone also. Nowadays, we are using drone a lot. Now you see from these remote sensing images, we need to process this data, we need to analyze the images, and then we can have a lot of information. And from these remote sensing images, there are many applications, but the three basic applications are geomorphological mapping that deals with the shape of the Earth's surface, then lithological mapping, that is the rock types in the Earth crust, and geological structures or the tectonics. These are the three basic applications. But there are many applications, those are focused and derivative applications, and those are very, very important, like mineral and hydrocarbon exploration, then groundwater targeting, construction material, like your marble, like your granites, like your sand, and then your stone chips, then the limestone, which is used for cement, then engineering geological investigations, like your hydropower plants, like tunneling, then environmental impact assessment, for example, is a big mine, open cast mine. Okay, so there are impacts. So what are the environmental impacts? So that also you can study using remote sensing. The geological hazards like landslide, like earthquake, like volcano. There are many these anthropogenic hazards, but the root cause is a geology, like your mining hazards, like subsidence, like coal fire. Like in case of groundwater also, there are a lot of geological hazards due to subsidence, due to pollution of water quality, isn't it? So there are many applications possible using remote sensing as well as geographic information system. Now coming to the basics, how we can identify rock types from remote sensing images. You know, there are three broad rock types: igneous rock, sedimentary rock, and metamorphic rock. This igneous rock and sedimentary rock, they are the primary rocks, but there are differences, isn't it? Igneous rocks are the crystalline rocks. They are massive, they are homogeneous, and they are interlocked because they are crystallized from the melt. Whereas sedimentary rocks, they are deposited. So particles are deposited, so they are soft. Their surface is smooth, so their texture will be fine. And because they are deposited at different times, so there will be different layers of deposition. So they will have some kind of layered appearance. And there are characteristic landforms like ridge valley, like these hogbacks, cuesta, plateaus, different kind of landforms you can have in sedimentary terrain. Then metamorphic rocks, they are basically formed due to pressure and temperature. And they are formed from the primary rocks only, like igneous rock or sedimentary rocks. When they are subjected to this higher pressure and temperature, so the minerals are recrystallized, minerals are aligned, there are some deformation features developed, there are some parallel alignment happens, and then these foliation plains, cystosity plains developed. There may be some geological structures like folds, faults developed. Okay, so because of these regional foliation plains, because of the parallel alignment of the mineral grains, so there will be these parallel weak plains. And along these parallel weak plains, there will be differential weathering, and which will appear as striations on the image. Now I have described all three major rock types or three broad rock types. What are their characteristics and how they should appear on the image. Now on the illustration on the right side, you see the same image. There are all three types of rocks are there. Now can you identify where is sedimentary rocks, where is igneous rocks, and where is metamorphic rock? This is basically this aerial, this remote sensing, and it is a black and white image. So from the black and white image, you have to tell. Now you see on the upper part where I am moving my mouse, see this Here the texture is very smooth, finer textures. There are some layers. There are a lot of dissections, so that means rocks are soft. So this is, whereas in the central part, see here, is it not massive? It is massive, homogeneous. Texture you see, it is coarse. There is a scoop out effect. These grains are scooped out. So this is igneous rock. This you can interpret broadly how I can differentiate between sedimentary and igneous rocks. Now you see this lower part, there are the parallel weak planes. There are the striations, isn't it? So this is metamorphic rock. Okay, broadly you can identify. Now coming to more samples, all are black and white, these samples only. See these two, top left, these two samples you see, very clearly you can tell these are igneous rocks and these are igneous extrusive rocks. These are the volcanic cones and these are the lava flows, lava threads, lava flow lines. Here also you can see volcanic cones, but here very interesting, this feature you can see, these are the dikes, intrusive igneous rocks. These are the wall rocks. Okay. Now coming below, see there are the prominent layering of the rocks. And the rock surface is quite smooth. There are a lot of dissections. There are a lot of these stream channels which cut these rock formations. That means the rock is very soft. So this is sedimentary rocks. From the layering itself and from the appearance of the rocks, you can tell this is sedimentary rocks. Now on the right side, the upper and the lower, both the samples are essentially metamorphic rocks. You see here the regional foliation planes, there are the joint planes, so that you can see here very clearly that showing some striation-like features. Now here you see regional foliations are very clear. Along with that, you see this is a geological structure. It's a folded structure, isn't it? So from this folded deformational structure, we can tell these are developed due to some stress. So due to higher pressure and temperature, so these metamorphic rocks developed, and this is the appearance of the metamorphic rocks on the remote sensing images. Now coming to this geological structure. So geological structures broadly like faults, there are different kinds of faults. In fact, faults, again, there are different types of faults in terms of geometry, in terms of their genesis, and then the lineaments. These are the fractures and joints. Okay, they're the linear weak planes with a linear appearance and unconformities. They can be mapped from remote sensing images using the tonal and the physiographic expressions. Now, what of remote sensing, you know? Here, remote sensing gives you the synoptic view of this geological structure. So the entire geological structure outcrop pattern we can see. Whereas if you go to the field on the ground, you can see only a small part of the structure. You won't have this complete view. You won't be able to see the geological structure in totality. But in remote sensing image, depending on your image swath and the spatial resolution, you can cover very large area or a smaller area as well. But definitely, with respect to the geological structure, you can choose the image swath and resolution, and you can see the geological structures in totality. So from the synoptic view, we can very clearly interpret geological structure. Like here, you can see very clearly there is a folded structures which is carved these sedimentary beds due to the pressure. It has been deformed. Now here also you see there are the trend lines or form lines. That is the bedding planes. You can see here, you can interpret, and this is the axis. This is the fold axis, and this is a plunging antiform. And this is also plunging antiform, but it is mostly a domal structure. Okay. Now coming below here, you see the illustration, the lower this left. This is very prominent fault. In fact, it is a tear fault, Yamuna tear fault, and these are the Sivaliks. Sivaliks are offset here by this Yamuna tear fault. It is a strike slip fault. And the right side, you see there are faults also, but there are mostly the lineaments. And these lineaments may be joints, like here. These the weak planes have some regular arrangements, but the other places they do not have regular arrangement. They are random and they are long. So they are the fracture planes. So they are in totality, these fractures and joints, they are known as the lineaments. Now coming to these geomorphology and landforms, you know, geomorphology deals with the physical processes and materials for shaping the Earth surface. And this landform is essentially defined by the topographic elevation, then the slope, and the surface ruggedness. And this is the unit of geomorphological study. You know, a landform is characterized by its unique topography, material composition, and structure. For example, you can see a landform here. This is alluvial fan. This is the Ghaggar fan. And this you see here, basically these are all houses. This is a city, Panchkula. Okay, near Chandigarh is here. And there is a Mohali. This Panchkula is completely, this alluvial fan is modified by the settlement. But this is a landform, alluvial fan. So this alluvial fan has a particular shape, particular size or geometry, and it has a particular elevation pattern, isn't it? So it has unique topography, material composition, and a geometry. Landform is a truly multivariate feature, and it is a function of rock types or lithology, geological structure, geomorphic processes, climate, and time. Time is also very, very important for the development of the landform. Now, remote sensing provides this synoptic view and the elevation related information about the landforms, as I have already explained, this alluvial fan. Now, in geomorphology, we study morphography, that is their shape, size, and this your composition, material composition, that is the geometry, and the morphogenesis, how they have formed, and the morphochronology. There may be different landforms. Then which landform has developed first, which is later, that comes under morphochronology. And then comes morphodynamics. What is the currently the active, the geomorphic processes? There may be tectonic processes. There may be some gravity-borne, gravity-driven processes, like your due to fluvial action, due to the aeolian action, due to glacial action. Okay, these are some of the physical processes may operate, and there may be tectonic processes also, like folding, faulting can also happen. Now see, in this particular slide, the illustration you see, this shows this fluvial geomorphology. See, there is the river. This is the area is from the northeastern part of India, and this river is the Barak River. See the landforms, very prominent landforms here, Oxbow Lakes. Okay. Here, very interestingly, you can see different landforms like alluvial plain here, whereas the floodplains are here. But floodplains also there are differences. Here is the older floodplain. Okay. This floodplain previously it used to be flooded. And there are these Oxbow Lakes, they are the natural levees. Those are basically paleo-natural levees. Now here you see this is the active floodplain. So presently the river is flowing here, and there are the point bars or channel bars. Now the right side you see this is the structural hills. This is not fluvial processes, but this is the tectonic processes as well as physical processes are operating. There are this trend alignment you can see of these parallel trend of these hills and valleys you can see here. And this is the extended view of this part that I have already explained to you, alluvial plain and the floodplain. Now coming to this thermal remote sensing, which is different from optical remote sensing. You know, optical remote sensing, this wavelength range is 0.4 micrometer to 3 micrometer, whereas thermal remote sensing wavelength region is 3 to 35 micrometer. And in this range, 3 to 35, there are 3 atmospheric windows exist. One is 3 to 5 micrometer, and another is 8 to 14 micrometer, and third one is 17 to 25. You can see in the illustration below. 3 to 5, this is one atmospheric window. This is the transmittance in white, and the black means absorption. Now it is, you see here 8 to 14. This is the major atmospheric window in thermal region. Okay, but here there is, you can see here somewhere around 9.5 or so, there are black only. So there is transmission is very less. Why? Because here there is the ozone layer that absorbs this electromagnetic radiation. Now you come to here, that is 17 to 25. There is one atmospheric window, but that is quite subdued, very small. Okay. Now you see this 8 to 14 micrometer, it is very popularly used, this your thermal region, for thermal sensing of the geological materials. But 3 to 5 is also used, but 3 to 5 and 8 to 14, both are used by airborne these platforms, whereas this 8 to 14, more precisely 10.5 to 12.5 micrometer spectral region is used by the spaceborne platforms. And this 17 to 25, this is not very important so far, and it is suitable for low temperature objects, and it is subdued atmospheric window and not well investigated till date. Okay. Now you see in thermal remote sensing, it is so far underutilized due to non-availability of data is one of the main reasons. So see, in geological materials, what are the rocks consist of? The major or the dominant rock forming minerals are essentially silicates, isn't it? And the silicates absorption peaks, they lie in the thermal region. Identify well. And carbonates also in the salt wave infrared region. But these silicates and also carbonates have prominent or characteristic absorption peak only in thermal region. But thermal region, we are not studying much. We need to study more, but with the availability of the data and the spatial resolution is another problem. In thermal remote sensing, spatial resolution is not very fine. So that may be another reason it is underutilized and data non-availability. Now you see, for example, here there is a broad absorption peak around this 10 to 12 micrometer. And from this absorption peak location for the wavelength, you can very clearly identify whether it is a ultra-basic rocks or basic rocks, or it is your diorites or cyanides, that is the intermediate rocks, or the acidic rocks, it's the granites. The pre-silica is there, or quartz occurs as minerals in the rocks. Now in thermal remote sensing, there are certain thermal properties of rocks are important, and we exploit those thermal properties or thermal parameters. Using those parameters, we can identify these rocks in thermal remote sensing. We can characterize these rocks, and they are like thermal conductivity, thermal capacity, thermal diffusivity, and thermal inertia. But out of that, thermal inertia is very sensitive and widely used, this parameter in thermal remote sensing. And this thermal inertia, if you want to measure it in the laboratory, there are a lot of things. You need to have thermal conductivity, you need to have the density, you need to have the specific heat, and it is a very cumbersome process. But in remote sensing, it is very easy. Inertia means resistance to temperature change with the supply of heat during the daytime from the solar radiation. How this materials responds to temperature change. Okay, so if you have one image during daytime, rather midday, and another image in midnight, you can get the temperature from thermal remote sensing image. So from two images, day and night, you can have the delta T. And if you can have the reflectance during daytime, so you can understand how much energy has been reflected back and how much energy is absorbed. And it is used to raise the temperature of the material. Okay, so 1 minus A. So maybe that is your energy balance equation, Kirchhoff's law. So in that case, so if you make 1 minus A, 1 minus reflectance, so that means the entire energy is used other than the reflectance for this increasing the temperature of the material. Okay, and if you see how it responds delta T, so then you will get the apparent thermal inertia. And using this apparent thermal inertia, we can characterize the material, whether it is a fine grained, whether it is a loose or compact, and what is the density of the material. And also there is another thing important is the albedo or reflectance, so the color of the object. Okay, so if the color of the material it is a black or it is white. If it is white, it will reflect. So this energy to raise or change the temperature of the object will be less. Okay, so these are the things you can characterize using thermal inertia. Now you see two images. This is basically optical image, pulse color composite 754 from Landsat TM. It was a color image, but I have changed into monochromatic image. Okay, just to compare with thermal image, which is basically brightness temperature image, which is monochromatic, only black and white. So for one-to-one comparison, I have made this color image into black and white brightness image. Now you see here, there are three major rock types: dark volcanics. These are the dark areas. Then the limestone, which reflects a lot of solar radiation, and these are the altered these rocks. Now in this thermal image, you see all this limestone which appears bright in the optical image are appearing dark. All these dark volcanics which in optical those are dark, here these are all bright. Okay, just the reverse. Why? Because how much energy is available to change the temperature of the material, isn't it? That matters. Now you see, if we have this multispectral thermal image, which is possible in case of spaceborne ASTER, which is possible in case of airborne sensors. This is an airborne sensor example, TIMS sensor. So it is operated by JPL. It has 6 bands, whereas in case of ASTER spaceborne sensor, there are 5 bands. So 1 band less due to the ozone absorption band. Now you see in this FCC image of this multispectral thermal image, you see color, isn't it? Different colors for different materials, different landforms. Why? Because different material have different composition, different compactness, different inertia, and therefore they have different temperature. And because of this different temperature, they are sensitive with different wavelength region. The material which has higher temperature, they will have more electromagnetic radiation in the shorter wavelength. And the material which is lower in temperature, it will have more electromagnetic radiation in the longer wavelength. So this is very, very important. So based on these sensitivities, you are getting different colors in the false color composite. We are getting this is the pink or red color alluvial fans. Where the compact rocks, you see blue. You see the soil appears yellow, isn't it? So different landforms, different your materials, different rocks or alluvium, they have different signatures in multispectral thermal image. Now, if you see in a volcanic terrain, there are different lava flows. These flows erupted at different times in the last 200 years. This is an example of this Mauna Loa volcano. Okay, and the FCC image you see, different lava flows has different colors. Why? Because they are erupted at different times. They are at different stages of cooling. Some of the lava flows are hot, some of the lava flows are cold. Not only that, their glassiness may be different, their texture may be different, so their temperature is different. There the soil formation has happened, which is old. There may be vegetation also started growing. These old lava flows, isn't it? So based on that, their temperatures are different. And as their temperatures are different, their sensitivities in different wavelengths are different. And we are getting different colors. And you can characterize very, very well how these lava flows erupted at different times. Okay. Now coming to this microwave region of the electromagnetic spectrum. So in optical, we are in the micrometer wavelength region. That is your 0.423 micrometer in optical. In thermal, from 3 to 35 micrometer, isn't it? Something like this. Now, in case of microwave radar, see, it is 1 millimeter to 1 meter. This is the wavelength range. In fact, in case of synthetic aperture radar, these are all centimeter wavelengths, like X band, 3 centimeter wavelength, then C band, 5.6 centimeter, then S band, 10 centimeter wavelength, L band, 23 centimeter, and if you go to P band, around 60 to 70 centimeter wavelength. Now, you see, in case of radar, radio detection and ranging, okay, so this is active remote sensing. So in case of optical and thermal, those are passive. We depend on the solar radiation, but here no. Here the electromagnetic pulses transmitted from the sensor itself. You see the red color, that is the pulse transmitted, and now it interacts with the Earth surface, and different times it is reaching the Earth's surface at different distance, and it is returning at different times. YOLO is the return pulse. So this is how radar's remote sensing is done. And you see, it is not vertically down. It is side looking in one side only, not both sides. You can have either this side or that side. And it is not vertically down, off-nadir. So these are the differences from optical remote sensing. It is off-nadir, side looking, and its wavelength is very, very long. The wavelength is centimeter. Centimeter means 10 to the power minus 2 meter. And micrometer, in case of optical remote sensing, 10 to the power minus 6 meter. So if you take a ratio of these two, it is going to be 10 to the power 4 times wavelength in case of radar remote sensing. So because of those differences, it has many advantages. There are certain disadvantages also. For example, because of its side-looking geometry and off-nadir, it is very sensitive to surface geometry. And that helps to provide information on geomorphology and geological structures, because geomorphology is very much expressed through the topographic elevation differences, topographic slope, ruggedness, and geological structures also, like lineament. All along the lineament, there will be linear depression, isn't it? Fault means there are some offset, some vertical offset, isn't it? There may be this horizontal offset also. Now, in case of radar, because here the pulse is transmitted and it is interacted and coming back. So it is a coherent remote sensing because of this coherent signal. So it is very sensitive to surface roughness. And because of that, we can characterize this surface well, and rock types, it is a function of the grain size or the fracturing pattern. And based on this grain size and fracturing pattern, different rocks can be identified. They may be discriminated. Again, it is very sensitive to dielectric property. The radar is colorblind. So in the radar image, you won't be able to see the color of the object. But what it does, it is sensitive to the electrical property of the material, rather the dielectric property. And dielectric property is nothing but this free H2 molecule in the material or moisture content in the material. So using this dielectric property of the material and its sensitivity in the radar image, we can have meaningful information about the unconsolidated materials, soils, like hydrated rocks and materials, altered rocks. For example, gosans in case of mineral deposits, sulfide deposits, isn't it? So those kind of areas can be demarcated from the compact rocks. And most importantly, radar, because of the longer wavelength, it can penetrate through vegetation, and also it can penetrate through ground also. Because it penetrates through ground, so it can image some of the subsurface features, like your buried paleo channels, active faults in the alluvial area. The faults you won't be able to see because it is obliterated, because the material is loose, but the fault is there underneath. So, but radar can penetrate. So you can have information, some subsurface information. We have some illustration, we'll show you. Some civil structures also, like water line, pipelines, oil pipelines, sewerage lines. And in the forest area, because it can penetrate through vegetation, you can have information of the terrain. Like you see here, some of the illustration. Here you see is Dehradun area only. See here, your micro topography is so much highlighted, but it has disadvantage. In a rugged terrain, it gives you some geometric distortion. So you see in the Himalayan region, it gets distorted. See, this is the Shillong Plateau. You can see there are one side is very prominent because the radar is looking from this side, and this side there are some radar shadow. Why? The signal does not reach this side. There are some distortion also because of the slope of the features. Now you see another, this is a mining area, the Dhanbad area coal pit. Okay, see these are the open cast coal mines because of the ruggedness, undulations, and also because of the water accumulations in the open cast mines. They are very bright, isn't it? All the open cast mining area looks very bright. See here are some structures, some carved features you can see. We'll have some illustration later, we'll explain. See the comparison with optical image, brightness image. So color image converted to brightness only. And the same area you can see in radar image, like it is in this C-band, and this is finer resolution radar sat image. Now see, here the tone is very uniform, but here there are some this noise, random this your salt and pepper effect, like, isn't it? These are speckle noise. Here you see very prominent. This white, dark, like salt and pepper mixed together, isn't it? So these are some noisy appearance you can have in the radar image. But you see the microtopography, dissections, the channels are very clear. It is not so clear here, isn't it? But here are some distortions you can have on the rugged terrain like Himalaya. Now, using this surface roughness property of the rocks, we can discriminate different rocks with a different surface roughness. Like in this example, you see, this is the limestone, hard and compact limestone, very rough surface. Whereas this is medium grained sandstone. Okay, so medium grained, so roughness is intermediate. Whereas here there are the shale and clay. So shale and clay, you know, geologists particularly, you know, shale and clay, they are finer sedimentary rocks. See it? Whereas sandstone is medium grained sedimentary rocks, and limestone is a non-clastic rocks, isn't it? But it is bedded limestone. So now it is very rough, and this is intermediately rough, and this is fine surface. So see, their brightness is different. So surface roughness is more, it is more bright, isn't it? So using the surface roughness property, you can discriminate rocks. Now in geomorphology, you see, if we use this radar image along with optical image, so this is basically a fused product. It's a merge of the optical multispectral image and the radar image together. Now you see, from the optical image, we are getting the spectral information of the materials. But the radar image, as we have merged with the optical image, so you have all kind of structural information, isn't it? Like structural, it's very prominent, and because radar can penetrate, so the buried channels are also visible here, isn't it? And some of the surface features, those are not prominent in optical image. You see here, these are the elongated features. These are basically the longitudinal dunes. So dunes are also very, very prominent here because radar image is merged. And this is basically an impact crater. The boundary of the impact crater is very distinct. Now see, this is your ISRO radar image, RISAT-1. But in case of radar image, there are different polarizations are possible. The like polarizations like horizontal, or vertical, and cross polarizations like horizontal, HV or VH. Now here we have examples of HH, horizontal, and HV, cross polarized image. Now see, in case of like polarized image, we get information mostly from the surface. So surface scattering features, like here you see the settlements, Dhanbad city, here the open cast mines, different surface features are very prominent. In this case, surface features are not, but open cast mines, all these open cast quarries are very, very prominent. But that is not our interest. Interest, you see, geological feature. See this same area I have extended here in the HH and the same area in HB. Now see, in this case, this particular feature is very, very prominent. What is that feature? This is a fault. Fault, subsurface fault, very near to the surface. But because of the land use practices, agricultural practices are operating over this area, as well as the thin veneer of soil layer. So this fault is now buried, is covered. But while you are using this HB cross polarized image, it can give you subsurface information. So here subsurface information, here surface information. So this is the beauty of radar image. Now I'm coming to the different applications of remote sensing. To begin with, remote sensing applications for groundwater studies. So one of the major applications in groundwater studies is groundwater prospecting or groundwater targeting. So where groundwater availability is more and where it is less, where you can drill a well and you will get water to pump, and where if you drill a well, you will not get water underneath. So this is what groundwater prospect or groundwater targeting means. So using remote sensing data, using their geomorphology, your rock types, geological structures, as well as some ancillary data like rainfall, like your water level or any other ancillary data you can use. But essentially rock types, geomorphology and geological structures, you can prepare a groundwater prospect map. Then other applications like recharge estimation, then your groundwater flow modeling, groundwater quality. For example, in this case, you see, is a part of the National Capital Territory of Delhi. You see here the potential or groundwater prospect and quality we have combined, where groundwater availability is more and quality is also good. Where groundwater availability is more, but quality is bad, not useful. So both the things are important. So we have combined both together and prepared a combined map, prospect and quality. Similarly, here in this case, you see groundwater flow. What is the groundwater flow? Which direction it is flowing? Isn't it? So those kind of information you can obtain from remote sensing and the geographic information system together. Now you see in from remote sensing images, we can use some kind of indicators for prospecting of groundwater. There are some indicators or some criteria or first order criteria, like features associated with recharge zones, like rivers, canals, lakes, ponds. So in and around rivers, generally we get water underneath. Why? Because from the river, a lot of river water recharging this neighboring region. So groundwater recharge is very good. So if you drill a well, just on the bank of a river, you'll get water if the this material is not hard rock, which can hold water, isn't it? Now, which are associated with the discharge zones, like if you are near a spring or other this effluent seepage, so then this water is coming from the aquifer. So these are the discharge zones. Then soil moisture is very, very important. Then the vegetation, because if soil moisture is high or vegetation is more, that means aquifer or the groundwater table shallow. So groundwater is available at the shallower depth. See it? And the second order or indirect indicators, which indirectly you have to interpret, like what are the topographic slope, what are the topographic elevation, what are the type of rocks, essentially hydrogeological properties of rocks, defined by the porosity and permeability of the rocks. Then what are the regional structures or different geological structures in this area? Then the fracture system, particularly in a hard rock terrain, like in the Precambrians. So where the rocks are crystalline. So there the fractures are very, very important. They act as the avenues for groundwater flow. So intersection of the two fractures, if you drill a well, you'll get some water. And if there is a long fracture, then water can come along this fracture and you can pump water. But water availability may not be huge, limited water. Then weathering depth, again in a hard rock area. Then drainage density is also important. And there are certain special kind of geomorphological features like sinkholes, alluvial fans, dikes, buried channels are also important. Okay, for different perspectives. For example, here you see, this is a alluvial, this your aquifer. Now you see the shibboleths. I've shown you this image previously. See in this part, this is Bhabar zone, and this part is the Tarai zone. You know that, isn't it? This is the Jamuna river. Now see in this area, this your image tone. What is that? Image color is very bright, white-like. So that means soil moisture is very low, and also vegetation is assigned red color. Near infrared band is assigned red color. So here vegetation is very low, soil moisture is very low. That means water table is deep. In Bhabar zone, what happens? Lot of water percolates down, but water availability is not near the surface. This water is flowing down as a base flow. But if you come down to here, Tarai zone, see there are a lot of soil moisture, there are a lot of vegetation. Okay, and also you see in this part of the river, there is no river water. It's a dry river bed. But if you come down to here, suddenly this water emerges on the river bed. Isn't it? So these are the effluent streams. Okay, so this water is coming from the base flow. So here the water is available very near to the surface. Okay, so that is the reason vegetation growth is more, soil moisture is high. Okay. Now in the remote sensing, along with remote sensing, we should have geophysical investigation. So if you have some geophysical investigation, then we can characterize the aquifer. So this is one example in the Mussoorie area, over the ridge. So initially from remote sensing image, we have identified the lineaments, which can this serve as a long avenue for the groundwater flow. And then geophysical investigation, we have identified there is the water is available underneath. The water is accumulated in the aquifer. So you can drill a well and you can get a lot of water. In fact, here almost 180 liters per minute water yielding is happening, but there was no water before that. So geophysical investigation along with remote sensing, these images are important. Now that is ground-based geophysical investigation. Now from the spaceborne geophysical, your investigation, spaceborne geophysical data like gravity is a space borne gravity like your GRACE, isn't it? The GRACE and GRACE follow on. So in this case, in 2009, this is the paper published by Rodel, and it showed that there is the severe groundwater depletion in the northwestern part of India. And 2014, again this another group, Chen et al., they have also shown this groundwater depletion is there, but the location is a little different. We have studied this entire northwest India, and we have seen it should not focus like this in one area like this here. In fact, this is the situation. Okay, so groundwater storage is not in one point here, but it is quite varied over this region. Yes, groundwater depletion is there in the northwestern part of India, but there are a lot of this variation is there, isn't it? And this is the in situ groundwater storage change that is based on this Central Groundwater Board in situ groundwater level data. Based on that, we have prepared this groundwater storage change map, and this is the groundwater storage change from the GRACE gravity, and you can compare this. Now, some advanced techniques like interferometrics are, it can tell you that some of the aquifers, those are overducted, means over extraction of water happens. So groundwater depletion is very, very severe, and as a result, the aquifer has got compacted, and so the land has subsided down. So we have number of studies, like in case of Mohali, Chandigarh, in case of Delhi, in case of Gujarat, in case of Calcutta, different areas we have studied. This is an example like this here, Mohali, Chandigarh area. See, there are a lot of groundwater depletion in Mohali, Landran, Kurali areas. This is pre-monsoon, and this is post-monsoon and pre-monsoon groundwater level data. Okay, and this is your Ambala below. So these are the area where a lot of groundwater depletion is happening due to the pumping out of water, and also it shows this aquifer compaction and land subsidence. Here is more precisely we have studied using advanced differential interferometric SAR technique, and we have shown how this land is subsiding in this area. And due to the subsidence, particularly differential subsidence of the surface, the houses which is above this land surface, there may be cracks, there may be damage, and we have characterized these house cracks in this Mohali, Chandigarh area. There are tensile cracks, there are the compressional cracks, there are the shear cracks, there are different kind of cracks are happening, or rather it happened. Now there are other applications like mineral exploration, and particularly surface minerals. Using the spectral properties of the minerals, you can identify mineral and therefore the mineral deposits. But there are predictive modeling also using different information from remote sensing images like geological structures, geomorphology, as well as spectral information of the minerals and rocks. We can also prospect the mineral deposit underneath. And also by geographic information system, you can have mineral resources information system. And different surface minerals like bauxite, phosphorite, okay, different minerals or iron deposits, you can prospect using the multispectral, but most importantly by hyperspectral remote sensing. Because hyperspectral remote sensing, because it is your sampling is shorter, around 10 micrometer to 15 micrometer. So this absorption peak can be very nicely, it can pick up. Like you see in case of optical remote sensing like visible and near infrared, 0.4 to 0.7 is the visible, and 0.7 to 1.5 micrometer is the this your near infrared region. Here you can have you can identify ferric and ferrous iron, manganese, copper, nickel, this kind of minerals. Whereas in case of Sweet band 1.5 to 1.8, 2.0, 2.4 micrometer, hydroxyl ions, carbonates can be prospected well. They can be identified using their spectral properties. Whereas in case of thermal infrared, as I already told you, 3 to 5 or 8 to 14 micrometers, silicates and carbonates, they can be identified. So this is the beauty of hyperspectral remote sensing compared to the multispectral remote sensing. You see this narrow absorption peak, you'll miss it in multispectral, but in case of hyperspectral, this your spectral profile that can be very easily picked up. So this mineral identification is easier in hyperspectral remote sensing. So here in case of hyperspectral image, unlike this multispectral image, they have more number of bands, at least more than 200 bands. And we are working in a hyperspectral data cube, which is made of some rows, then columns of data and number of bands on the z-axis. Now, similar to hyperspectral remote sensing, microwave remote sensing is also very important for mineral exploration. Particularly, it identifies the geological structures. It highlights the geological structures like faults, like fractures or lineaments, and the shear zones. Okay. So from a radar image, we can get all these geological structures very nicely. Now, if you combine with the optical image, so this multispectral image is merged with the radar image. So if you merge these together, then what happens? We get both geological structures and the spectral properties, that is the composition of these minerals. So by combining these two, this information content is more than double. So mineral, your prospects, we can more precisely, we can identify where the mineral prospect or mineral deposit prospect is high. Now, this remote sensing is also very much used for petroleum exploration. Elementarily, for example, sedimentary basin identification, rock type identification, geomorphology or terrain analysis, geological structure, these are fine that you are doing for in other applications also. But here, the one more important one, another important factor is the spectral absorption properties of the hydrocarbons or hydrocarbon index that you can use, and the soil or vegetation which is contaminated with oil or this retarded growth of the vegetation, that can be very nicely picked up from this spectral absorption properties of the hydrocarbons. Like here you see from the geomorphic anomalies, here river you see shows a circular anomaly. River suddenly it goes circular. So that means there is something wrong. There is some geological structure underneath. And if you do some geophysical investigation like seismic profile, if we do that and interpret, then we can understand. So the top surface of this hydrocarbon trap is something like this, and there are a number of faults exist. And this is the final interpretation. You can see there are some antiformal structures or anticlinal structures. Okay, so it is the hydrocarbon trap, oil trap, and this is in northeast near Silchar area. Silchar is shown here. Okay, so here there are oil prospect was identified based on this. First, from this remote sensing based geomorphic anomaly, followed by geophysical investigation. And then you see there are some spaceborne your geophysical parameters like gravity. Sometimes it helps to identify these wide oil fields, because wide oil field means low gravity zone. So in low gravity zone, you can identify where these oil fields can be identified. Now coming to some of the geological hazards as a sample, like landslide. So there are different types of landslide happens, and particularly we are very close to the Himalaya. So there are many landslide happens in the Himalayan region, like the falls, like topples, like slide, like spread and flow in terms of the type of movements. The type of the material, that can be rock, that can be debris, and that can be soil or earth materials. Depending on that, there may be different kind of landslide. Again, depending on the type of the slip surface, these movements can be straight or movement can be curved. So this is translational, rotational. The landslide can be active, it can be dormant, it can be stabilized. So different kind of landslide is possible. But we are mostly interested in this identification of the active landslide. So from this scar on this earth surface, we can identify there is a recent landslide has happened. So from the scar on the Earth surface, from the no vegetation, so from by visual interpretation, by image segmentation, or advanced technique like this multitemporal change detection. So based on that, you can identify this landslide scar. Again, there are different criteria for old and dormant landslide. There are a lot of criteria are there for this potential landslide zone identification. So there are a lot of studies required, and many people are working on that. This landslide susceptibility and landslide early warning system. So there are some of the areas where presently the researchers are working, particularly for landslide early warning system. Okay, so here you see in the satellite image how a landslide looks, and on the ground terrestrial image, terrestrial photograph rather, you can see how it looks. So this is a rock fall in Gopeshwar in the Garhwal Himalaya near Chamoli, and this you see on the satellite image. Rock fall due to the earthquake, Chamoli earthquake, it occurred long back. Now you see, this is like a spoon, isn't it? So this is a rotational landslide. The landslide is coming like this, spoon-like. Now this landslide susceptibility zonation is very important. Landslide hazard zonation, okay, that we did it for the all these pilgrimage route corridors in the Uttarakhand and the Himachal Pradesh area, also in the northeastern part of India. So, and we have identified some of the high hazard zone, and this high hazard zone was identified just before this Uttarkashi Varunavut landslide, 2003. So in 2001, we prepared this map, and 2003 there are this massive landslide happened here, like this. See here, there was no landslide, and here you see like a trident landslide happened. And again, using high resolution aerial photographs, we have studied once again, and finer scale this landslide, this your susceptibility or landslide vulnerability we have studied. As I told you, we have also studied from in the northeastern part of the country, from the Shillong to Aizawl area. So all along this belt, we have studied this landslide hazard zonation, high hazard, moderate, and this low hazard areas. And you can see some of the field photographs of this your lithological formation, the ridge valley like this. And here you see there are some wedge failure, or rock fall type landslide. Now, see the advanced techniques like interferometrics are, it can tell you just before the landslide, slow movements of the terrain before the landslide, it can show you. But this rapid movement, sometimes it cannot, but the slow movement it can. There's some samples. This study published long back in the late 90s, and this study in the early 2000s, you see here these landslide movements can be mapped. Okay, just before the landslide. But here, what is required then? Slow movements, if we can measure, if we can monitor a landslide, this your prone zone, then we can tell when the landslide is going to happen. So that is the key of the early warning system. But there are other things are also important, like geophysical and geotechnical characterization. Where is the slip face? Where landslide can happen? Because this part is hard rock. Here sliding will not happen, but here there are this material is loose, unconsolidated, which can be slided down easily. So the slip surface needs to be known, and the slow movements needs to be known. Based on that, we can model a early warning system, and which can work well. Now, if we study earthquake, for example, this Nepal earthquake, which occurred in 2015, see there was the main shock 7.8 magnitude, and there are many aftershocks 6 and above. These are the aftershocks locations are shown, and some of them are greater than 6 magnitude. And finally, on 12th May, there is a major aftershock of 7.3 magnitude. Okay, here in Kodari village. Now, how this main shock and aftershock is this damage causes the damage to the terrain, so that we have studied in Nepal and in the Indian part. And for that, what is primarily required? How the land surface was displaced due to the earthquake, movement over the land surface. So that can be done by differential interferometrics that we have measured immediately using immediately after the earthquake. We used RadarSat 2. Then Later on, we use allos to L-band, and you see very clearly this is the area which was uplifted around 1.65 meter uplifted. This is Kathmandu, and this area it was subsided and subsided about 60 centimeter. So it went down and it came up. This area came up, and this area went down. And due to this major aftershock near Kodari, you see this area was uplifted, this area was subsided. But not only this displacement, but also there are some other parameters are important, like what is the shear wave velocity of the material, what is the peak ground acceleration, what is the subsurface material structure, if there is any geological structure exist in the subsurface. So for that, geophysical investigation is required. That we conducted by this your ground penetrating radar, by this your this engineering seismograph or MASW. So based on that, we have studied this shear wave velocity pattern and the subsurface material properties, and then you can characterize well what kind of damage could take place and what kind of damage has actually occurred. Now see, in case of active tectonics, where presently there are some movements over the Earth's surface is taking place along the previous these your faults. So that can be identified also, but first by this geomorphic anomaly, like but the river shows some kind of anomalous pattern, like you see here, straight river, isn't it? Here you see river was initially it was meandered like this sinuous, but here suddenly it got straight. So that tells you there may be some active faults in these locations. Here you see topographic break, very clearly topographic break you can identify, isn't it? So here if you do some geophysical investigation, geophysical survey like GPR, ground penetrating radar, or ERT, electrical resistivity tomography, or other techniques to get the subsurface information. Or you can have also trenching, that means drilling here all along a line. So geophysical investigation is important, as I have already explained to you. This GPR, here you see the fault, and then this IP resistivity. So that helps you to interpret the subsurface information. Now, similarly, there are other geological hazards like your coal fire. Coal fire, the detection and monitoring can be done in thermal remote sensing. We have studied all the coal fields in the Gondwana, and more particularly the Jharia coal field. And the spatio-temporal dynamics of the coal field we have studied for many years, starting from the 90s, from 1992 to still 2019 or 2020, we have studied. And here in this side, surface coal fire locations we have studied from the shortwave infrared images. And here the complete plan, where is the surface coal fire, subsurface coal fire, open cast mines, abandoned mines, where are the washeries, all information we have put together. And here how we did it. This 2005 surface and subsurface coal fire, 2013 surface and subsurface coal fire. You see this is the same fire, analog photograph. In 1990s, this photograph was taken, and this is later, but this is the debris fire. Similarly, in a coal mining area, the subsidence or roof collapse is another major problem. Because of the underground mining, because of the underground coal fires, because of the waterlogging, subsidence can take place, roof collapse can take place, and casualties and loss of properties can always happen, and it happens. Here we have studied using interferometric SAR technique and using different bands, C band, L band. We have studied these subsiding areas and compared with the ground surveyed map. You see, this is the rate of subsidence in centimeter per year. And these are some of the ground photographs. See, this is the subsidence is happening due to the coal fire underneath, and here due to the mining underneath. Now, we little bit we'll glance through the planetary missions, remote sensing of the this planetary surface. So this journey begins for ISRO and for this Indian Institute of Remote Sensing with the launch of this Chandrayaan-1, this mission, that is 22 October 2008. And there are many sensors, and one of the most important sensor was the Chandrayaan-1 M-Cube, and similarly now Chandrayaan-2 IIRS. Those are useful for spectral analysis. Now from the spectral analysis, we can get the composition of the material, like calcium percentage, like iron oxide percentage, like TiO2 percentage, and optical maturity. It tells you this when this crater has been formed, whether this crater is recent or the crater is old, depending on the maturity of the surface. If the maturity is very low, that means it is this new crater due to new impact. Whereas if this maturity is very high, is highly matured material, when the optical maturity index is high, that means it is old material. So that means here the impact took place long back. So all kind of information you can have. Along with that, it also helped us to discover water on the moon. And using the IRS sensor presently, we have more confirmatory evidences we have got to tell that the water exists, although in the volatile stage, so not as a liquid water, exists in the lunar surface, deep inside the craters. Now using the microwave remote sensing also, we can characterize the lunar surface. The geometry of the craters is scattering properties rather. Scattering means whether it is made of the loose materials, whether it's made of the regolith materials, or it's made of the rock fragments, fresh rock fragments rather. So that means it's a rugged area, or it is the smooth surface where surface scattering takes place. So that we did it using circular polarization image, that is compact polarimetric SAR image. That here we have used the parameters like circular polarization ratio, degree of polarization, and also polarimetric decomposition. For example, M-chi decomposition, M alpha decomposition. Then if we compare, then we can characterize this lunar surface. What is the surface properties? What are the material properties? So this is what we can do. And also not only surface, but also the subsurface is possible using some of the radar sounders. Like in case of this LRS onboard Kaguya Selene, that is the Japanese mission. It gives you information about the subsurface also. Okay, because radar can penetrate. Okay, so depending on the wavelength, isn't it? So you are getting information about the subsurface also. So how the layering is there underneath, if there is any geological structures or any tectonic features are available. So all kind of things one can do. See here, this is an optical image of this your double impact crater that is in Libya, southeast Libya. The same area, if you see in a radar image, how they are different. They are so subdued appearance, but here the geometry, their expression is so prominent, isn't it? So with this, I will close. So before that, there are not only the remote sensing data, but you need to have a lot of this your instrumentation, lot of field data, lot of geophysical and geochemical this your survey required. Here are some of the samples of this your field observations, what we are conducting. Like we are using spectrometric analysis using spectrophotometer in the optical region, in the thermal region from the samples. And we also facilitate that. If you need some kind of analysis, you can also approach. So depending on the requirement and this your genuine this thing purpose of this thing, we also do this spectral analysis. We can do it for you. Okay. Similarly, there is the engineering geological laboratory we have where you can have direct shear test. We have geophysical instrument like GPR, ground penetrating radar. We have ERT, and we have this your resistivity. So this is here, and then a number of core stations. We have more than 15 core stations we have. The total stations and many these geophysical and these geotechnical instruments we have. Some are also we have fixed on the field as a field laboratory like extensometer, like piezometers, like thermal gun, the thermal imaging camera, so many things we used to do along with the remote sensing image from the satellite, from the aircraft or from the drone. Okay, thank you. So with this, I close my lecture. Now I'll take your questions and for discussion with your queries. Thank you.